Uh, this directory structure essentially is this set of nodes, which are again some part of your hard disk, some specific parts, which points to the files. What are files here? These are basically just spaces like physical blocks on your hard disk. And both this directory structure as well as the files reside on your hard disk. Great. So we need to actually understand the design, the structure, right? What are the data structure or basically not. So what are the structure and what the directory should provide? So in general, when people design directories, it came up after it came to this position that we have today after almost 30 years of work. And the constraints that people added was from pretty practical. At the beginning, the computer was used by only one person. Think 1945, think 1950s and so on. Then multi-user came, multi-user wanted more files, the requirements increased. So the system model, that is the requirements of the system, a directory system would be like there are multiple users in a machine. Think like you have a shared machine and each user might need a bunch of files. Okay, it sounds obvious because if you go to the department server or go to software lab, you have an account. Just like Rajat has an account, Nisarg has an account. So all of the users on the same machine, and each one of them wants to have a bunch of files in their, say, in their home directory, or you have the subdirectories, and they act independently. Nisarg cannot tell Rajat that don't create that file, don't write that file, read that file, and so on and so forth. That sounds reasonable? That's a shared system, nothing special about it. But these are something that a directory needs to support. From this, like 3 constraints, what people came up with that these are the desirable properties of directories. There are 4. First one is efficiency, that is locating or searching a file should be efficient, right? Because it's just an index. From index, you should able to go to the files pretty soon, pretty fast. The second one is the naming should be convenient to user. And what does convenient mean? 2 users can have the same name file. All of you are working on assignment 5.cpp. And you want to work on the same machine, of course, like it's a lab machine. You don't want to name your file assignment 5 slash nisarg.nisarg.cpp. Why? If like every user might have 2 users can have same name for defined files, or defined defined name of same files is also important, but this is one which is very basic. The third one is grouping. That is, you might want to put all of your movies in one place and all of your codes in another place and all these things. So there has to be some way in the directory to group. And the last one is more advanced, which is sharing these files between users or programs. So at least this first 3 needs to be supported by any directory structure. The 4th one is optional, but modern operating system, they do support it. And we'd see how. But so this is efficiency, that's the basic. Then naming, 2 users should have the same file name, 2 defined files. And grouping, these 3 are requirements. Any questions? It's pretty straightforward. Now let's see how to do it, right? That's the point. So what happens at the very beginning when the multi-shared system, the Multics came in 1969 or 1970s, then they just had like, a single directory for all users. For example, here you have, say, 5 users, and all of their data is dumped into one folder in today's abstraction. So the problem is, if I want you to search, say, mail, the file mail, the file name mail here, you need to do a linear search. That's the very basic. Like all the files, a flat file structure. All files, one directory. There is nothing else. All users, all files. So 2 different users cannot have the same file name because the file names are identifiers, and you cannot have 2 mail files in the same directory. It's a flat structure. The third one is there is no grouping here. Like, the mail is going with records and taste and it's all over the place. So this is a single level directory structure, which essentially doesn't solve any problem that today's users want. But this is the start. And this is what people built up. How? So after the single level directory structure, people came up with, okay, that's the really real beauty of the abstraction. They actually came up like, hey, this is not working. So why don't we just take another level of abstraction? Why don't we actually give separate directory for each user and put their files in those directories? It's only 2 level. There is no multi-level subdirectory, blah, 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 nothing. Previous one single level, this is 2 level. And what it does is that, so there is a master file directory, and for each user, there is one entry. And for each entry will point to another user file directory. And within that, you will have your files. In this case, user 2 have 2 files, A and data. User 3 has 2 files, A and test. Remember, these are again directory entries. The actual data is this round things. These are in the physical storage. So the good part is that the moment they actually have this abstraction, like take one level up, user, and then their files, it becomes a tree. We know how to handle trees. Efficient tree traversal, no linear search, no fancy data structure. So the good part is efficient searching. And you can definitely have now same file name for multiple users. How? Because now your directory entry is basically the whole path from root to the node, to the leaf. So before it was only the file name was only test. Now it is user3/test. That means that both user3 and user4 can have a file called test. The problem is, again, there is no grouping. Meaning, still, this user1 have cat and test in the same folder, which looks different to me, at least by the name. So there's no semantic way to actually group those folders. So any idea how to solve the last problem? So this tree structure solves these 2 problems, right? Efficient tree searching using traversal and tree properties. You start from root, you basically go down and find whatever is needed. And also you can have the same file name for 2 different users. How to solve the third one? There is no grouping capacity yet.
Introducing more levels. Yeah, one more level.
Exactly. Why one more level? Go in levels. But essentially the idea is that why 2-level tree? Tree can be n level. Let's make it n level. So this is called tree structure directory, right? And the idea is, again, extremely simple. You start with the root. That is what we used. That is what we use today with some modifications. But essentially, you start with the root. Root will actually have, say, here 3 folders, 3 directories. Each directory will point to some subdirectories. Some subdirectory will point to other subdirectories, and the loop goes on. Remember, all these directories and subdirectories are basically pointers to disk location. Like this directory disk location point to the subdirectory disk location. And then finally, it will point to file data. You need to know what is file and what is directory. There are metadata too. When it starts creates the directory structure, it stores what is file and what is directory. Now, the one key thing to note here is that in this tree structure directory, you now have to give the full path to specify a file. It is not only the even previously you could have told like user1 logged in and looked into the mail like this file. So create an environment for user1. In tree structure, you don't need to create any environment or anything. You just give the full path. Otherwise, you cannot handle it. It's just like in arbitrary number of levels. Any questions? So essentially, if you understood it, that actually means that it solves these two problems. Like it is definitely efficient searching. Two users can have the same file name for two different files, assignment 5 for all, like for each of you. And finally, of course, the grouping is possible now, right? Like within movie subcategory, you can have, I don't know, Hindi, English, Korean, and there you go. The user have some way to group their data. This tree structure also gave a new concept of absolute or relative path, like absolute or relative path name. So that's why this, when you actually saw, like when you code, you talked about path name, right? It's not file name, like give me the full path of the directory. This is why you call it a path. It's a tree structure. It's ultimately a path in the tree. And to make it simple, to give abstraction to the user, because if the user has, or you have, say, 6 level of subdirectories for whatever data, you have to write the whole thing again and again. That's tiresome. I'm not talking about GUI. Even for GUI, you have to click again and again. So there is the concept of absolute and relative path. Absolute path, the full path. Relative path, relative to the directory that you are standing now. Meaning that if you want to just do change directory to say spell, then it will be relative to your current directory, the present working directory, or PWD as it's called. If you understood this, how would I know that what is a relative path and what is an absolute path? Yes and OS. I need to do a CD, right? I need to actually change the pointers and put the user to the right subdirectory. How do I know whether something is a relative path and what is an absolute path? Perfect. Can you speak up? So, because there are people, so Rajat's answer was that the absolute path will start with slash. And relative paths will not start with anything. It's like a null character, essentially. Why?
So an absolute path means it starts from the root of the tree up until the file that you're specifying. So you have to, since you're specifying the entire path, it will start at the root directory, which is always slash.
The root is conventioned to call slash. That's the reason. So if you start from root, it's a absolute path. If you don't start from root, it's a relative path. The way to navigate through directories is essentially CD or CHDIR in your Windows, PowerShell or something. In Linux, it is CD, and it basically does a tree traversal to find the right directory, where to go, or the right file. Now, in tree structured directories, one problem that does come up is about deletion. You created the directory, but you also need to delete files. The problem is when you start deleting, it is fine when you start deleting a file. You give the full path, it will just do its magic, like remove that disk space and allocate a disk space and get like it's free. Nothing special about it. When it's a file. However, what if it's a folder? So you can create a folder with mkdir or make directory command. Pretty standard. And essentially you will do a mail and then count, like within a directory mail, you create a subdirectory count by doing an mkdir. You should remember it is extremely useful, and you perhaps already used it in your first assignment. You need to. The point is, after creating all these directories and subdirectories in your tree, how do you delete a subdirectory? Deleting a file is easy. You just deallocate the storage space. How to delete a subdirectory? The question actually comes because if you want to delete, say here, I'm showing you a directory mail, and there are 1, 2, 3, 4, 5 subdirectories. Now the question is that if you delete mail, will this be deleted? I wrote something there, but I just want your opinion. Should it be deleted?
Yeah. Otherwise, how you will access it? Which strings?
So essentially, if mail is deleted, you're true, but you are correct, absolutely. Otherwise, how would you say that mail is deleted? Because of the grouping capability. So even thematically, your these 5 subjects are part of mail. So if mail is deleted, everything should be deleted. So there are 2 ways of handling the deletion. For MS-DOS, I'm not talking about Windows, by the way, MS-DOS, the olden 80s. They will not allow you to delete a subdirectory unless all the files are deleted. So you go in within each subdirectory, delete files, and then go up and then like up at the subdirectory and then delete the subdirectory. Extremely time consuming, but that is how it was handled. Even if there is at least one file, you cannot delete it. And then in Unix gives a recursive option, rm-r. What rm-r does is different than what rm does, actually. So essentially, it actually goes through each directory level. It handles directories specifically. It removes the directory entry and then go up in the hierarchy, in the tree. But essentially, it recursively deletes that particular directory and all its subdirectories and files. So Unix gives you just a shorthand of what MS-DOS asks you to do by hand. But ultimately, the concept remained. You cannot delete a directory unless all the subdirectories and the files are deleted. And here, by deletion, you should understand by now, or even feel by now, deletion is just mean deallocation of the space from the directory structure. Because you cannot delete, like if you have 500 GB hard disk, you cannot delete 200 GB from it. It's like deallocate, free it, put it to some other use. Questions on the tree structure directories?
So there is also a -f flag which forcibly removes.
Yes, it does.
So what's the difference between that and the recursive one?
So if you do rm-f on a directory, what will happen? You have to do rm-rf. That's the standard command.
Okay.
rm-f is to handle to tell ways that I don't care, the user doesn't care, even if the file is opened by someone else that's related. If there's data corruption, I'll take care of it. Because files can be opened by other programs, no? So rm-rf is it's a really bad comment. But any case, questions on this? So far, 3 directory structures we studied: single, two-fold, two-level, tree. Now in tree directory structure, essentially people actually try to do the last, more advanced, try to give the more advanced guarantee, which is sharing files between users, between directories. And with that, they actually came up with something called this acyclic graph directories. Essentially, in after your tree structure is done, you can actually add some links between the files, between the this directory entries, so that 2 directory entry will point to the same physical location. That means that now this storage space can be accessed by both /dict/count and /spell/count. It's extremely useful. Why?
Safe space you want to have.
Sure, but then again, saving space is, well, I can imagine, but this is something not about saving space. Anything else? Shared libraries, linking to them, aliasing them. If you haven't used aliasing, it basically means renaming or basically creating just a name for one executable or one file. Extremely useful for most of the ways to function. So handling shared libraries. Essentially, for doing the acyclic graph structure is a fancy name for just to add a few links between the nodes of a tree, right? So that two or more subdirectories or directories even point to the same physical space. And for that, you need to have something called a link. Link is again a fancy name of just saying that I will just add one pointer to a directory entry to a specific disk space. And of course, when you try to access a link, you need to do the traversal, you need to follow the link. Nothing fancy in it. But there is something fancy about how the link will be created. So in a tree, you are just creating more advanced links. So there are two types of links. And listen to this carefully because this is something apparently quite confusing to people. So there's something called hard and soft linking. Okay. So essentially, a hard link is when both, by the way, hard link and soft link, both are essentially, the idea is same. You actually say like, give me a hard link, meaning that give me a hard link named link one. It means it will create something called link one, which will point to a data location on the storage. That's the basic idea for both hard link and soft link. But how they deal with it is very different. The usage are very different. For hard link, essentially the operating system will create a mock file entry and point it to your actual storage space. Write this, that it will actually create a FCB and then it will point to the FCB. What is that? We'll have the whole next 2 lectures to learn, but just note it down if you're noting this. But essentially, operating system creates a new file which points to that same location. First, that is hard linking because you are directly, you are not really caring about the existing directory structure or anything. You are just pointing it to the actual storage. For soft linking, of course, you don't want to do the actual storage. You want to just point to the operating system pointer, which points to the actual storage. Because the operating system needs to have, like, if an operating system is accessing a particular file, that means it has essentially a pointer to that particular storage space. When you do fopen, fwrite or something, it has pointer to the second, like this storage space. What soft linking does, it will point to the pointer of the operating system. I know it's confusing, but it is important. Hard linking directly point to the storage space. It's another name of the same file. If you say the file as a storage space, like some parts of the storage space, like 5 MBs, hard linking is just another name. Soft linking is a pointer to in the operating system entry, which points to the storage space. It's a 2-level pointer. Now, hard links cannot link directories. With this knowledge, can you tell me that why hard disk was asked not to link directories?
Directories are an abstraction over the actual.
One reason, yes, good. Any other reason? That's true. I mean, directory is just a metadata, right? I mean, if you want to just create a hard link, which is just another name, another file to the same location, why would you even go for the other directory structure? I mean, that doesn't make sense. Both has different capabilities. Soft link is directories used by operating system and so on and so forth, blah, blah, blah. That means just give a pointer to the pointer that operating system uses. So hard link always refer to source file, even after it's moved, destroyed when the file is moved and so on and so forth, because it's just another file. So even if when you run, say, if you move a particular file from one block to another, the operating system will adjust the pointers. Hard link will also get adjusted. It's just another file name, another name for the exact same location. Soft link, on the other hand, when a file gets moved, operating system says like, yes, move function is done. So the pointer is invalid. So soft link will get invalid when the file is moved. Because it depends on the operating system. If operating system is moving a file or invalidate it and don't do pointer manipulation, which it does not, soft link doesn't really work. Now, yes, question.
So if I'm creating after moving that file, I'm creating another file of the same name. What would happen to this sibling?
That will be an attack.
So that will go.
Yeah. So essentially that will require something called you need a race condition. Yes, that will work unless the garbage collector kicks in and tells like, hey, there is no file here. Remove all the entries in the operating system. Operating system needs to know when the file is deleted, and it will clear the entry from its own memory that file is deleted. There's something called a race condition and Tokta vulnerability, which basically says like, let the operating system work on something else, and I'll just replace that file sneakily before the operating system clears up the file. TalkTau stands for time to change from time to update. Yeah, TalkTau, TOCTOU. But you're absolutely right. So at some point, operating system will do the bookkeeping. But if you can actually stop it for a moment and replace it sneakily, the sibling will be really an attack vector. You think that you're opening a PDF of your lecture, you are basically opening a malware. But you need to have a race condition with the operating system. And by the way, this is an attack because how you would actually do the race condition, even that is described in the attack. Okay, any other questions? Hard link, soft link, simple concept, but understand it clearly.
Like, what are the use cases where we prefer hard links and where we prefer soft links? Or we always prefer soft links?
We generally prefer soft links. That is basically the God's honest truth. Like if you look into your operating systems, the soft link will look like a file name, and then like if in your Linux, you do an ls with a soft link. Try this comment yourself actually. You would see that it actually shows like a link name and then arrow and then the actual file name. Operating system can do it because it's a pointer to the file, like the file entry in the operating system. For hard link, you cannot do that. It's like just like another file. You cannot do that. The operating system cannot show it. It's just like another file.
So hard link is an older concept which is not removed yet.
Hard link is an older concept. It is not new. It has some use cases. I would have to look up exactly where hard link is used today, but because it's not dead yet, it definitely has some use cases. Symlink are the ones like hard link, symbolic link, soft link, symbolic, and symlinks are the one which you will generally use. Now, actually, let's actually see. This is quite a bit of a concept. So, any questions about it? On the other side, hello. Can you guys hear me? Perfect. What will be the parent directory of soft link directory? So for the soft link, wherever you create so that's an interesting question, Aryan. So whenever you create a soft link, say in a directory A, the soft link will reside in that directory. It can point to another subdirectory B or somewhere else, but it will reside in wherever you will run the ln-s command, or wherever path that you will give to the ln-s. Okay. Does that answer your question, Aryan? Thank you. So after hard and soft linking, you understand that this tree structure, right? You need to actually ensure the acyclic property. Now I just made a statement that you need to ensure the acyclic property of the tree. But clearly you might or might not, depending on how you are linking. Like for example, is this acyclic? There's like there are soft links here, right? And so yeah, this is acyclic. Yes, because this is like directed. You have to remember that directory goes to subdirectories. This is a directed graph. It's not an undirected. Otherwise, there is a cycle already. So the question is that if not acyclic, what will be the problem? The example that I gave you is referring to acyclic. That's like a toy example. But if not acyclic, then you would have the infinite depth problem. What does it mean? Essentially, remember that all you do for saying that how many files are in a directory, all you do is tree traversal. Simple stuff. Start from root, go from left, right, and simple. However, if there is a cycle, then suddenly you are going into a loop. And even after tree traversal, which doesn't finish, you actually report that there are infinite number of files in that directory. Yeah.
So if there are no shared directories and no shared files, how can there be a cycle then? Because then a path will end at that file, right?
Yes, I'm talking about when there are these soft links or hard links. Basically, there are links. So yes, if there are no construct links, this problem will not even come. But as you might have known, symlink, or basically creating the symbolic links, is essential for your operating system or your softwares to work, to have shared libraries, to have executables that everyone uses. So the point is that you have no idea how many nodes are in the tree, and that also means that your like estimate of how much space is used is totally messed up. How do you know how much space is taken by your file system? You traverse the tree, go to every single node, say how many spaces there, you do a count plus X. Now it is going into infinite depth. So you have no idea how much space is used. Big problem. An example that I gave here essentially, I mean, this is how you generally do it. Bad idea. Like you have a directory A, and then within that you create a symlink within A called C. C will point to A. And when you would actually try to do a tree traversal, like what is the size, using something called a du minus h command or such du command, it will just go in infinite loop. If you follow symlink, like A by C, A by C by A by C by A by C. I actually run into this problem a lot because sometimes what I try to do, say I have a directory called paper. Within that, I create a directory called temp. And going to temp, I do cd temp and cp minus r .. paper. So I try to copy the parent directory in the directory itself. I do it all the time. And I always, and at least in my Mac, what happens is that after a while, after 3 minutes or 2 minutes, actually like it reaches the maximum depth, cannot copy. It tried to do the tree traversal. Actually tried to do the tree traversal. It always does. And at some point when it reaches the depth of 500, it stops, like 500 subdirectory levels. Cannot handle more. So that will be, so CP might still be okay because it's in my hand, I am doing stuff and the implementation is not really taking care of it. If you want to know how much space is used by your hard disk, this definitely is a problem. That's a crucial piece of information used by operating system and everyone else. What do you do? Essentially, there are two solutions. One is that do not allow links to be created to subdirectories. Will there be still soft links if you don't allow creating links to subdirectories? It will point to the pointer which points to the file. Simple. Soft link has nothing to do with directory or files. It's basically just like I'll just point to the OS. Whatever OS does is good with me. Now, the second solution, this is a bad solution, real bad one. The second solution is that every time you create a like ln minus s, I'll run a cycle detection algorithm in the whole directory structure. What's the problem with that? It's expensive, extremely expensive. So it might not be possible. So what is the solution that you proposed, which is used today? Remember that all we care about is to know the number of files in a directory using the tree traversal. Cycle creates a problem, and cycles can happen. What would you do? Or what do you think the current operating system does?
This like size in the metadata of all the directories in the path.
That means that you need to do some bookkeeping when you create a link. Expensive. You need to actually look into the cycle. No? I mean, in one way or other. It's a good thought, though. Ideas?
Won't do anything when you are traversing till a certain level. Stop.
That's what Mac does. Yes, that's what Mac does. You got a cycle, but after 500, you just say, okay. Have a hard bound on that. However, even that will not solve your problem, Ashutosh. For CP minus R, it does. Says like depth 500, I'll stop. For finding the size of all of your files, it won't work. What did you say? I went to 500 level depth and find 500 MB is used. That doesn't mean anything to the user. It is approximate. In some case, you cannot do approximation.
While finding sizes, don't go inside the symlinks. There will be a path which will lead to the file which is the original one.
If there are hard links?
Difficult to identify. But still, hard links also can be detected. Operating system knows that it is a hard link, right?
Yeah. Essentially, bypass links during directory traversal. So it will know that it's a link, of course, like it's a link that is created, and bypass those links during the directory traversal. Simple. And even for hard links, if you're going to the exact same memory, like a storage location, you just discount it. You cannot double count, of course, and that is pretty easy to do. Pretty easy to not do. So that is the solution. Remove the links while doing directory traversal. That means there is no links. It's a tree structure, easy to traverse. Everything is good. Questions? Okay. So we learned about the directory structure, started from single, and we came this far about the whole linked tree directory structure, like tree and then adding links into it, hard and soft. So this would be enough for you. That's surprising, but this is all there is for your directory structure. Finally, a tree structure with links. And using the links, you can do magic. Literally, you learn that in advanced operating system. Like as I mentioned, one is top-down vulnerability. You do a race condition with the OS and change the file which is linked to, and you have vulnerability. There are ways to actually do some sort of workflow attacks in symlinks, because symlinks are the ways for me to change your file. I'm not kidding. That's all there is to it. But now you have a directory structure and you know exactly how files are created. Or actually not created, but what are files? There is some files like book chapters, you have an index. That is a file system. Now, let me ask you this. You have your thumb drive, you created a whole file structure in it, like meaning a directory structure. Directories, subdirectories, within that there are files and so on. Just like me, you took out the thumb drive, went to your lab, went to your home, you put the thumb drive in. How do your operating system know there is a file system? The operating system has its own file system, right? So there has to be some sort of plug and play kind of thing, right? In the file system itself. Because remember, like in one file system or one partition, you have to be able to navigate using a tree structure. You start from the root and then you go down, 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 and then you should be able to access the files on your thumb drive. Because for thumb drive, I cannot write a defined mechanism, defined structure. It has to be plug and play. Okay. So for that, you would need something called file system mounting. Extremely simple concept. Why simple? Because it's a tree structure. There's the beauty of simplicity of data structures when you're using simple ones. So essentially a file system, say your whatever resides in your thumb drive, it must be mounted before it can be used by your operating system. And an unmounted file system is mounted at a mount point. Don't be afraid of the lingo. Essentially, it's just a way of saying that it needs to be mounted, it needs to be added to one node in your file system. Let's depict it. In A, I'm showing you that this is the root directory, right? This is the root directory. And then you have the users, and when that Bill is there, Fred is there, Fred is asking for help in one file. Now, and then you actually have in B a new file system, which starts from this node, and it will go to Sue, Jane, and then Jane will have something like program, and then doc, and so on, subdirectories, like a whole directory structure. This is unmounted. It needs to be mounted. So essentially, you'll create a mount point. That is what, like, first we need to tell the operator, when you try to actually mount something in your operating system, you need to tell the operating system what to mount and what to mount. So there is a command called mount. You basically say the command mount and then this node, address to this node. And then you will give the address to the thumb drive, like in the /disk or /device. And all operating system will do is to add a link from what you just told to add a link from the first, what you just wrote, like the first parameter to the second parameter. That's all it does. That is called mounting. So you'll just merging two trees. And one tree will have only one root. What do? You'll create one node in the first tree, put the second tree there. The moment you use the tree abstraction, right, the file system concepts become easy, to be honest. And that is why it is used. So to wrap it up, we are just about time. To wrap it up, essentially, what are the data read or write abstractions that we learned today? Essentially, we learned about the file structure, what is stored with the files, look into stat and all these things. We learned about directory structures today, important. And ultimately, directory is your tree. And it comes with all tree properties with hard and soft links. And finally, we learned about mounting, like how to add those new file structures to your existing file structure. Create a node in your existing file structure, file tree, or directory tree, add an entry there. Okay, I would stop there, and tomorrow we will talk about what are the application programmer interface. Very simply speaking, what are the functions that you have to give for this particular structures to efficiently use it. I'll stop here and please ask questions.
What happens to permission?
Great question. So I forgot your name, sorry. Animesh, right. So Animesh's question is that what happens to permissions when going for the, like doing the links, right? Like any links? There's a reason I asked the question. Hard link or soft link?
It's
seems to be like soft link is a way to bypass it.
Not quite. So for so file permission, we haven't covered yet. That will be like a very small micro lecture at the end, a part of it, of course. But essentially, what is file permission? A file can be accessed by a user. It's basically telling which user can access what file. Nothing special. So if I recall correctly, for a hard link, the permission is same. It's stayed. For symlink, it does not.
Means that
The symlink file. So what I mean is, when you create a hard link, it's a file entry, right? So what would be the int? What is the like? What do you call it? What will be the permission on that file? Who own that file, or what are the group permissions and so on? For hard link, it is essentially an FCB that points to the exactly same storage, and it will actually copy the original FCB's like the permissions, if I recall.
So what's stopping me from creating a hard link to something in the root which is protected?
The operating system. It will check that what are the permissions. So we'll actually see in the implementation, when if you try to do something like that, the operating system will check whether you have the permission, like write or read permission to that particular directory. And if you don't, it won't let you do it. Does it make sense?
So let's say I want to, so can it be like if I do not have the write permission, but I have the read permission? Like, can I create a hard link?
You have write permission, but you don't have read permission.
I have read, but not write.
No, I mean, you can, but the original one will be owned by the other user, and the permissions will be the exactly same, right? For example, Animesh is creating a hard link to Nisarg's file, and Nisarg's file essentially is writable only by Nisarg, not by Animesh. So Animesh cannot write that because the permissions are same. He can read it, of course, using that link.
The reason I asked that write reversal, I ignore links.
Yeah.
How does it know kahan se access?
Kaha se a symbolic link? I think can you please elaborate that?
So like,
Go ahead.
when I directly open file and I use the hard link in my code. And but why it knows like, when it will try to find that file, it will not use hard link for traversal, right?
It will use no links while traversal for specific, like finding the size and all the other. Yes, for traversal, while doing over the directory, going over all the files, it won't really follow the hard links. Yes, or any links.
So it does. So does it follow? So like, if I have a hard link to a file and I'm trying to open it in my C code, so does it mean that when the operating system tries to find that file to like push the content into my code, does it follow the hard link or does it follow the original path?
It will, okay, I see what you're saying. It will follow the, I actually have to check that out. But if I recall again, it will follow the hard link, but it will also check permissions. And the permissions for the original file is not writable by you. Like it's not writable by you, so you cannot write that. But I need to double check that. That's a good question because it is pretty complicated. We'll see.
Sir, I think the confusion is that when are the links ignored and when they are not. That is
true. Let me try to actually look into it and give you a better answer. Because what I'm saying now is what I remembered. It's always better to go back and consult the docs. I'll do that and get back to you. Thanks for the question. Okay, any question from the other side? You guys are terribly silent today. Cool. Let's